Hello, ladies and gentlemen. Thank you for coming to my talk titled One Doesn't Simply Write a Stable BOF. So, we'll be talking about what are BOFs and why should you even care about them and how do you stop them from crashing. So, the agenda of this talk will be two main questions. Why do beacon object files or BOFs fail and how do you save your BOFs from failing? And before starting all that, you might think that who is this guy standing in front of me talking about something called BOFs? And in order to answer that, this is me, and I am a graduate student at UTS, and I am someone who you might call as a wannabe malware analyst or reverse engineer. And I have some hopes and dreams, so please don't be hard on me. And I am also CRTO, CRTL, and OSCP certified, and I have worked for the government of India before. And lastly, I am a foodie and a huge coffee nerd. So, leaving that, we'll be starting on the topic. First, we'll go through an introduction and a brief history of what are beacon object files. So, as you can see, beacon object files are small compiled C programs or COF object files for C2 beacons. And C2 beacons can be thought of something as Cobalt Strike or Havoc or even some open source platforms such as Mythic or Sliver C2. And what beacon object files do is they allocate memory within the implant, do some relocations, generate structures, then pass the execution to the BOF's entry point, which is usually the go function as it was in Cobalt Strike, but it can be different for different C2 platforms. And then official Cobalt Strike documentation states that Cobalt Strike parses the object file and acts as a linker and loader for its contents. So this is the official documentation stating, but it usually doesn't matter. Beacon object files are like vast in scope. And lastly, beacon object files allows operator to write shellcode that runs in process. And on the slide there, you can see a small flowchart. This is a very generalized picture of how beacon object files work. You can see that they run BOF as a position independent code, which can be called as shell code. Then they allocate memory region. They change the memory protection from either RWX to RX and RX. Then beacon object file sections are copied to memory and they are relocated and resolved. Then after that, depending on the configuration and the malleable C2 profile of the C2, it can either use beacon data func trick, which is essentially copying the BSS data section into the r.text r data section and taking the data from there, or it can use get proc address on its own to dynamically allocate Win APIs. Then after that, it just executes the functions and the malicious things, and it can lastly tear down everything. But you might ask, but hold on, man, why use them in the first place? Like, why do I even need to care about something called beacon object files? So to answer that, we need to go to the history books for some brief history. So before a beacon object files, a technique named fork and run were used to run implants. And fork and run meant that implants were run in a new sacrificial process, and the output of that sacrificial process was piped back to the beacon using named pipes. And usually it was like running for a long time, but they were not stealthy and they were easily caught by endpoint solutions because the detection surface is frankly very huge. Like there's process creation, process manipulation, data output, and creation of named pipes, like getting of data output from named pipes. The detection surface is large, so they were easily caught. And in order to solve that, beacon object files were developed. And WWE fans may get the reference here in the picture. So they are very extremely stealthy, and the only trace that they leave is the memory fragments of implants, which can only be caught by when the EDR solution scans the beacon process itself, and at that point it's not even that worth it to scan it because they know it's a beacon process. So they can just close it. But beacon object files come with a huge caveat that they are way more unstable and dangerous. This is due to the fact that they run in the main process memory thread itself of the beacon, and if something happens, like it crashes or like there's some overflow of data, it just crashes the whole beacon itself because it's in the main memory. So after that, we come to the first main question of this talk. Why do beacon object files fail? Like, I mean, there should be something wrong, right? So there are quite a few reasons actually. Like there's first one is architecture mismatch, which is compiling for x64 but running it in x32 systems. Then there's uninitialized globals, which usually meant that there's a BSS segment in the PE of a process that the beacon object file cannot access. And usually when you initialize global with a non-zero value, like either null or like you can do int x and semicolon in C, it usually allocates that in BSS section, which cannot be accessed by the beacon object file and it crashes. Then there's unsupported standard functions, as beacon object files are COF object files, so they don't have the C runtime, which means that functions such as malloc, calloc, or every like printf, everything, they are not available in the beacon object files itself. Then there's heap allocation issues. Then there's stack usage and recursion. If you increase the stack more than 4 kilobytes of data, and if there's deep recursion in the beacon object file itself, then it might lead that to a crash. Then large switch and jump tables. Well, this is not that big of a problem anymore, because it was when memories were less and the difference between the code section and the data section were more than 4 gigabytes of data. They usually, the data overflowed into the code section, which led to a crash, but it's not that big of a deal anymore. So it can be a bit of a big deal in x32 systems. And lastly, there's relocation limits. The amount of data can be relocated in a BOF. But the main problems are exception handling and misused beacon APIs. So due to the fact that they are small COF object files, they don't have the runtime, and due to that they don't have advanced C and C++ features such as structured exception handling or _try, _except. Then there's also VEH, which is not supported in beacon object files, and using those will just break the loader. So it's not worth using it. And misusing beacon APIs can also cause crashes. And you might ask, what are beacon APIs? So as I said before, beacons hold BOFs, and BOFs, in order to make the creation of BOFs easier, beacons and C2 platforms usually provide some APIs, such as beacon download, which can download stuff from the internet, or beacon parse, which can parse some data from the disk. And if you misuse them, it can just cause a crash. Then we know why do they fail. So how do I save them and also save hours of headache and misery during an engagement? So we will do 10 steps in order to fix the beacon object files, but these are not that difficult. These are just kind of basic programming constructs and also some niche BOF tricks which I'll be telling. So first of all, it's the basic stuff: compile correctly. So you will have to use the official compilation flags and toolchains for the BOF, because it depends on the C2 provider, and always try to use -c flag to a COF object, because -c during compilation creates a COF object, and you shouldn't use an executable or a link against libraries such as DLLs or SOs. And then you have to ensure that you target the same architecture as the implant. Like if you are targeting 32-bit, then you should create a 32-bit BOF. If you are targeting 64-bit, then you should create a 64-bit BOF. And finally, you have to follow official C2 documentation and compilation. Second one is you have to test for loader and framework differences. So there are a lot of different C2 frameworks and there are a lot of BOF loaders, and they all handle edge cases differently. So for example, if a BOF works perfectly fine in one loader, doesn't mean that it can work perfectly fine in another. You will most probably experience a crashing issue, or it might return a garbage value, which is not that required. And this usually happens due to unsupported sections or relocation types. It depends on the C2 platform itself. And Finally, in order to solve this, you have to target your BOF to the loader you are using, and you have to test on every intended platform. And if it's possible, try to create a modular version of the BOF so that you can just swap out stuff from each other, and it will make your life easier. The next is to properly use beacon APIs. As I said, they help the beacon object file to port some of the functionality to the beacon itself, so it makes the life of the developers easier. But misusing them are like landmines. I mean, they will crash at the most unfortunate time. And in general, you have to treat beacon APIs as black boxes. Think of them as they just take a value and return a output. Don't think of anything internal. Then you have to check the return values, avoid null pointers, zero out structures whenever needed. And some of example would be like before initializing a structure for beacon data init or beacon data parse, you can just zero out their structures, which is beacon data int f, yeah, and then you can just use them with the beacon APIs. The next would be the initialized globals. So if you need globals, usually try to avoid them, but if you need them, you have to give them a non-zero default value. And that can be done by using int x equal to 1. You can give any value here instead of just doing int x. And this should this ensures that the BOF loader will include the variable which is int x inside the image rather than relied on the unhandled BSS segment. And BSS segments offset usually changes between compilation flags. So I mean, if it's one offset in one compilation, it might be different in another. So you have to like try to avoid BSS altogether. And the golden rule is to avoid globals altogether and try to use only primitive variables, or else your life would be like from this raccoon, like from breakdance to breakdown. And the next one would be to limit stack uses. If you remember that I said before that if stacks are more than 4 KB, then they usually cause a crash, and you can avoid that by avoiding large local arrays or deep call stacks, and just avoid recursion altogether. You can use if switch statements, but try not to use recursion. And if there are large functions in your beacon object file, you can minimize them by breaking them into smaller ones, or try to use small buffers, or alternatively you can allocate needed buffers on the heap instead of stack. And heap memory is basically unlimited in the beacon object file. The next would be to avoid unsupported constructs due to the fact that the C runtime isn't available in a beacon object file, or rather a COF object file. So you shouldn't use SCH or even advanced language features such as like generics or everything. So you should not use it and try to stick to plain C. And if C++ is like required, then you should disable exceptions and real-time type RTTI, and mark the go entry point with beacon APIs with extension C linkage. This ensures that the beacon object file will first try to use the C part of the program, and then it will go to the C++. And lastly, avoid dynamic memory allocation of C++ objects because calloc and malloc are not available. And then you have to be careful about strings and Unicode. This is mostly dependent on the platform itself. Some platforms such as Cobalt Strike and Havoc, they usually include both Unicode and ASCII, but some other niche platforms such as Havoc, there's some new platforms which try to use Unicodes only and instead of ASCII. So you can encode the arguments as ASCII, and if the beacon object file calls Unicode APIs, you should pass Unicode or convert the strings before passing them to the beacon API. And as a general rule, try to explicitly specify string encoding when passing arguments. This can be done, like for example, there's virtual process alloc AXW, which is for Unicode, and virtual process virtual process XA, which is for ASCII. So you can explicitly specify them, or you can just encode them before. And then the eighth one is not a beacon object. Okay, it's not a beacon object file specific thing, but it's more of a general programming thing, and it's to checking all pointers and ensure that they don't give a null pointer. And you will also have to check the return values of the Win32 API calls. And also lastly, do not dereference a null point value, because it will most definitely be a crash. And ninth one is just a friendly reminder to use helper libraries and tools. The cybersecurity community is very huge, and you can already find many stuff in there. And you can refer to official documentation and read it thoroughly. And use some tools such as BOF lint, which can statically analyze a compiled BOF for common errors, such as unsupported sections, unresolved symbols, large tags, and exceptions before you even run it. And you can use that to statically analyze a BOF before even testing it, so that you might make the testing process easier. And last but not the least, you have to test thoroughly, which is in a controlled and lab environment. You can use a cough loader or a non-intrusive implant such as a dummy beacon while testing. And a common tip is to usually write the code as a normal executable, then try to run it, find out every programming mistakes in that, and then you can convert it to a beacon object file to isolate object file related issues. And lastly, you have to test it under a real loader to find out the issues. So we come to the conclusion of the talk, and here I will be giving you some of my final keys and takeaways. First one would be to treat a beacon object file like operating system kernel code. Just as you are working on Excels while writing device driver code, you have to do the same to a beacon object file. And remember that every null reference or a bad jump is fatal. And debugging a crashing BOF usually means replicating its conditions in a safe environment and tracing where the access violation occurs. And try to follow community best practices and official documentation. And you have to always remember that a simple mistake in a beacon object file can crash your beacon and end the engagement. So that will be all, folks. Thanks for coming to my talk. Here are my details if you want to contact me, and this is a link to my website if you wish to see what other stuff I am up to. Thank you.